Welcome to Meme Gen Monday here on Answer Everywhere. This is a live show, live improvised show where we jump into a source code repository and poke around and try to get a feel for what's going on inside of it. Today we're looking at the source code for gRPC Python. We've looked at gRPC before, so if you look in my on my YouTube channel, there you'll find the gRPC video. And on Meme Gen Monday in general, what we do is we look at code from the Google open source ecosystem, things that have been written and typically designed by Google and then open sourced. And gRPC is, of course, one of those things. So the reason I want to look at gRPC Python in particular is I want to get a feel for how one might add new gRPC language bindings, language implementation. And for several of the official Google implementations, those implementations are achieved by writing essentially bindings to the C++ core library via some foreign function interface. For other languages, I think maybe Go and maybe Java, the implementations are not calling out to the C++ code. I think at the very least, those they have their own repository that's not part of the official gRPC C repository that we've looked at before. Okay, so this is the gRPC repo that we already looked at. But now we're in source Python, and we're going to restrict our attention to source Python. All right. Okay, so I don't know where the name gRPC IO comes from, but this seems to be a combination of gRPC and input-output. And that seems to be what the Python library is named. Until I learn otherwise, that's what I'm going to guess. And here's the... We're just in source/Python, and I'm guessing that the most interesting directory is going to be gRPC IO itself. And the other directories we have are admin, channel Z, CSDS. I'm not sure what CSDS is. Maybe that's CSDs. But we also have health checking, reflection, status, testing, and tests. I trust Google to, in general, have a lot of tests and a lot of high-quality tests. So I'm not going to do a testing gut check like I do for other repositories that I'm not, that I'm not familiar with. I think in this case we've looked a little bit at the tests in the main repository. So there should be nothing essentially new there in terms of getting an overview of how the repo is laid out and whatnot. And status and reflection and health checking in channel Z, I recognize as all implementations of these kind of like gRPC add-on services that you get out of the box. So on the gRPC video that we did, I believe we looked at the the protobufs, the protocol buffer definition files for channel Z, and possibly also for health checking and reflection. And I think we looked at a little bit of the status stuff. So I'm guessing that that's what these things are. I'm not sure about admin or CSDS. Let's take a quick look at those before we get to the main event of gRPC IO. Okay, so gRPC admin interface package. So something about debugging gRPC library, channel chasing metrics, gRPC IO channel Z, and client status discovery. Okay, so CSDS is client status discovery. All right. So here's a snippet to create an admin server. gRPC admin.add admin server self server start. So this does seem to be like some sort of service you can add to gRPC. I'm not sure what exactly it does, but we have the init.py, which has channel Z and CSDS. And maybe admin is really just a combination of channel Z and CSDS. Did I look at setup? Yeah, so the requirements are, yeah. So I'm going to guess that that's basically what's going on. And then CSDS, which is not what this directory is. Here's CSDS. Client Status Discovery Service Package. It's part of the Envoy XDS protocol. Okay, so this is we also mentioned XDS previously in the previous gRPC video, which I will link in the show notes. And this is something about client discovery. Let's see, allows the gRPC application to programmatically expose the received traffic configuration. Okay, let's take a quick look at the proto, because I'm not familiar with it. So status, client status, listener config, cluster config, root config, scoped root config. All right. Not sure really when you would use this. I'm not sure if it was originally part of like load balancing that used the client information. Who knows? Surely somebody knows. I guess we can do a quick search for documentation. It seems to be Python specific. In short, it's an XDS configuration dump protocol. Can I get non-Python answers? CSDS.cc. Okay. Client status discovery service. I think this is what I just looked at. Okay. Well, whatever it is, it's for discovering client statuses. Not sure when you would use it, but you know, if it seems like something you might be interested in, I guess you can check out the documentation. All right, so here we are in the gRPC IO directory, and we've got a few kind of like straggler files, support version commands, and I'm hoping this is just command line parsing. Command error, Sphinx documentation, poison extensions, file name, gather, class gather, command to gather project dependencies. Build. Command build ext command to enable compiler specific flags. Try Cythonize. Okay, so these seem to be, these do kind of seem to be commands for some tool. I'm not sure exactly which tool. Command to generate documentation via Sphinx. Okay. So you can do things like generate documentation and look at dependencies and whatnot. So here's how to install. Here's troubleshooting. Cool. All right. Let's go to the gRPC directory. And underscore Cython is, so Cython is this like compiler that helps you generate code for connecting your Python and C or C++ application. So this should be where the interface between Python and C++ is defined. AIO, I vaguely recall. I don't remember what it's about. I guess we'll look at it. Framework could be important, could not be, could be not important. And then we have a bunch of Python files, but actually the number of Python files is pretty limited. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on the order of like 15 or so. And they all have underscores. And so I think that means that they're exposed somewhere else, possibly in framework. Let's look in the main directory again to see if there's anything that's exposing them. Core dependencies, parallel compile, patch, spawn patch, commands, support, gRPC version. I don't think any of the commands are things like run a server, right? So I don't think this is the thing that exposes all or imports all of the other modules. Okay, cool. So let's look in Cython. And maybe let's pull Cython out on its own. All right, so we have gRPC, which I'm going to guess is just a conventional name for the gRPC Python Python bindings. All right, here's the gRPC Cython layer. This tells you what Cython is. It's a superset of the Python language. So superset meaning that anything, any valid Python is also valid Cython. But there are Cython source files that are not valid Python, with extensions for dealing with C types and a tool that transpiles this superset into C code. It's got static typing, which can dramatically smoothing this Python C interop by allowing the fluid use of APIs from in both from the same source. See the wonderful Cython website. Okay, let's see the wonderful Cython website. All right, so this is the Cython website, and you can donate to them, I guess. And they've got documentation and whatnot. Okay. Let's see who their GitHub sponsors are. Does it say? Or does it have corporate sponsors or just individuals? Okay. So yeah, you can, if you're into Cython, I guess you can kick them some dough. All right, so here's gRPC in this directory, and then let's look at these two things that might be entry points, the pyx file and the pyxd. And let's see. Let's see what these file types are. So pyx or py is compiled into by Cython into a .c file. So if it has pyx, that means it's going to be converted to C. The .c file is compiled into a .so file, a shared object. Okay. And then what is pyd? Was that the other one? Oh, pxd. So pxd's files work like C headers. In addition to the pyx files, Cython uses pxd files, which work like C headers. They contain Cython declarations and sometimes code sections, which are only meant for inclusion by Cython modules. A pxd file is imported into a pyx module by using the C import keyword. Okay, so pxd is, what is the D for? I don't know. I don't have a good mnemonic, but it's the header information. And the pyx, I guess let's move these out of the way. The pyx is the more like the implementation file. It gets compiled to a C file. So let's look at the header stuff, I guess. Okay, so we're including a bunch of stuff from underscore side gRPC, as you would expect. Arguments, call, channel. So these are, this is worth looking through because these are the things that you would presumably need to implement if you're making your own binding. So this is relatively bounded. It's not everything in gRPC. So we have arguments, call, channel, credentials, completion queue. We looked a little bit at the gRPC completion queue, which had a somewhat clever design. And if you really want to understand gRPC performance, I expect that you need to have a pretty good understanding of the completion queue. Just my sense. Don't know for sure. All right, we also need events, which I don't remember if these are I think these are gRPC events and not things like keyboard events, but we'll see. Metadata, operation, propagation bits, okay. Records, security, server, tag, time, vtable. So we do need like vtable access and hooks. Okay. And then we're also going to include gRPC event. I don't know why it's down here and not up here. They're both pxd.pxi files. Wait, do we know what pxi is? Look up pxi. Okay, and literal include files. So, okay, so pxd is declaration files, according to this website. And literal include files are pxi. The distinction is similar to C and files and H files in D, to .c and .h files in C, I think is what it's trying to say. Okay. All right, something about includes. and they're slightly different from PXD files, I guess. So the following PXI files are part of the AIO module. And we've got completion, queue, RPC status, gRPC AIO, callback common, call, channel PXD, and server PXD. And they all have an AIO prefix. So let's look up AIO just to see if this is something that's documented. Async. So it's, I guess it's to let you know that it's asynchronous IO as opposed to like blocking IO or something. Okay. Fun times. Cool. Okay, so this was the what seems to be the main entry point. That's essentially its header. This is going to include all the stuff from the underscore gRPC directory and some AIO stuff. Here we are in the PyX, which should be like the implementation file for these things. And this should contain, if I remember Cython correctly, it will contain basically nothing. Look at that. Okay, we're going to eventually call initialize, cdef initialize, cdef extern. I think cdef initialize means that we're that this is an externally defined function in a C file. Yes. Okay. So here we are in what is it? What did it call it? The amazing Cython site, I think. This version is the latest and greatest. Okay. Okay. So extension types, aka cdef classes. So two different types of syntax. I guess I'll ignore that note until I need it. Wait, are you going to tell me what a cdef is? So there's Cython-specific cdef classes, which was designed to make declarations concise and easily readable from the C++ perspective. Based on what Python calls a built-in type, however, Cython supports a second kind of class, extension types, sometimes referred to as cdef classes, due to the Cython language keywords used for the declarations. They are somewhat restricted compared to Python classes, but are generally more memory efficient and faster than generic Python classes. The main difference is that they use a C struct to store their fields and methods instead of a Python dict. Okay. This allows them to store arbitrary C types in their fields without requiring a Python wrapper for them, and to access fields and methods directly at the C level without passing through a Python dictionary lookup. Okay. So, if I'm understanding this correctly, this actually is a definition of a function, but it's a cdef thing. So it's going to bypass Python dictionary stuff, and it's going to store all of its fields and stuff in a struct. Cool. And what is it going to do? Initialize, we have Python callbacks called by C core threads. This ensures the GIL is initialized. PyVal init threads, PyEval init threads. So this is some thread initialization function. And I assume that this is what the comment is saying. The Python callbacks are called by C core thread. So that makes sense because when the C code has callbacks. And so if you're calling it from Python, you're somehow stuffing Python callbacks where the C code is expecting C callbacks. And by calling PyEval init threads, we ensure that the GIL, which should be the global interpreter lock, is initialized. Well, let's double check what the GIL is. The Python global interpreter lock. Is the interpreter lock a CPython thing? In CPython, CPython is the, it's not a Cython thing. CPython is the main Python implementation, right? In CPython, the global interpreter lock, or GIL, is a mutex that protects access to Python objects, preventing multiple threads from executing Python bytecodes at once. Yeah. So it's this lock that hopefully you've never run into, but I have, and it's usually not fun. Okay, so gRPC set SSL roots override callback. And it's got this, this looks like C notation, SSL roots override callback. So whatever this is doing, I guess it seems to be calling a function called set SSL roots override callback to whatever this is, which seems to be maybe a reference to a C function. I don't know. And then, so we've defined initialize, and then we call initialize, which is going to do that stuff. And then cdef extern from python.h has this function init pyeval init threads that we called down here. So that's all that's going on. We include some stuff. And we include some more stuff. And that's really it. All right, so let's look at the underscore gRPC folder, which is here. So this is more PXIs, which should be the includes, ends in I, seems good. And then we've got the AIO directory, which is maybe stuff like callbacks. Call. Oh, okay, so we have PXD PXIs and PyX PXIs. So maybe I'm supposed to be looking at the first file extension to see whether this is an implementation or a header. I'm not sure. Okay, so what do we want to look at? Let's look at call channel credentials completion queue, CSD's event fork gRPC.pxi. Let's look at gRPC.pxi. And where did I just switch? AIO. Get rid of AIO for now. So we're going to look at gRPC.pxi and things that seem a little bit hard, I guess. So the vtable, the threads, let's see what's going on with the completion queue. And call is so fundamental that I'm just curious how it goes. Okay, and then init py, is this empty or is there a lot of work here? Okay, yeah, it's basically empty. Okay, so here we are in the vtable. Do we want to be here first? I don't think we want to be here first. We're going to be at gRPC.pxi first. Okay, so here's gRPC.pxi. We're several folders deep. We're in underscore Cython underscore gRPC. All right. So we'll C import libc.time. And I'm guessing C import just means once this file is processed, this is a C import. It's going to like hash include some stuff. And a bunch of type defs. So S size T is int pointer T, size T is uint pointer T. These I think are the fundamental type, right? On the left. And these are the defined type. Let's look up the syntax for C type def in Cython. Type def defines a type under a given name. So the example they have is C type def int star T. So this must mean that int star is the primitive type and T is the new type, right? Okay, that's what we thought. Then we have some C++ utilities. And we do the cdef extern stuff. From queue, namespace standard, no GIL. I don't know what, oh, no global interpreter lock, I guess. And then we're going to cdef a CPP class Q of T. And we've got Q bint, bint, maybe, oh, bint I think is like Python binary int thing. bint is a Python thing. Convert binary to text input. Basically, what I want to know is this bint like a C? I expect it to be like a C int and not a the Python integers are basically strings, right? They are they don't overflow. They're not like they don't have a max. You can keep adding things to them, and they don't have the same performance characteristics as C strings. So I'm thinking that bint should be more like a C string since we're in the C bindings, but I just wanted to double check. An optional Python bint, optional Cython. So maybe bint is a Cython thing. The special bint type is used for C Boolean values. Okay, so it's a Boolean. All right. Oopsie. Oh, no. All right, so it's a Boolean for empty, whether it's empty. We've got a front and back, and they both return type T, whatever we passed into this, essentially a template. And we could pop and push and get the size. We have this note. Note, unfortunately, we can't use C import here because Cython links it with exception handling. It introduces new dependencies. Okay, so there's some, man, I don't know. So somehow C import causes Cython to link something with exception handling. I don't know if Q, so this is a standard Q. Okay. And so we're just defining our own like Pythonized version of it because I guess by default, and there's maybe no way to disable it, the C import handling turns on functionality that we don't want, namely exceptions. They don't use exceptions in C++ code at Google, so they don't want the Cython to add them. We've got a mutex. Standard condition variable. Again, these are all no global interpreter lock. The mutex unlock lock, condition variable, notify all, wait. Okay, so this is threading stuff. gRPC core declarations. So we are cdefing a bunch of stuff, I guess, that we didn't C import. And these are things like alloc. And we've got GPR malloc, zalloc, free and realloc. gRPC byte buffer read. Struct. We don't care about the internals. Pass. Okay. They're going to import codegen gRPC types.h. So the code generation types maybe. gRPC h and slice reference unref slice gRPC empty slice, more slice stuff, malloc, etc. Declare functions for function like macros because Cython. I guess because Cython is maybe a reference to the maybe this thing here, or because something else that interferes with macros. Oh no, it doesn't seem like we're doing the import trick. So this is maybe just some other Cython annoyance or limitation or whatever. But we've got gRPC slice start pointer, gRPC length. So this is all stuff to handle gRPC slices. We looked at gRPC slices a little bit before in our gRPC video. Some constants, a clock type, monotonic, real-time, precise, or time span. Okay. A time spec. TV, I don't know what TV is, but we've got seconds and nanoseconds and a clock type. And more time stuff. And let's see how long this is. This is a long file. Go to the bottom here. So 729 lines. I wonder if they wrote this all by hand. But let's just flashing through. We've got server credentials, session cache, SSL session cache, more server credentials, call credentials, gRPC channel, call error. Okay. So this is a lot of stuff. Try blame. Cython refactor of Python C wrapper layer 8 years ago. Fix most of licenses. Okay. Attempt to not depend on standard int.h. This is where the C type deps came from, is trying not to depend on standard int. Fix Python Windows build. Let's look at the refactor from 8 years ago. We get a so we're adding a bunch of stuff. I'm not sure how to quickly use this interface. I'd like to see some deletions and stuff. Well, I don't know. Okay. So they certainly added a lot of stuff. Did they add? Let's see. We're look at gRPC.pxt. Did they add this whole thing? I guess so. What did they delete? I'm not sure where it came from. What does yellow mean? Does yellow mean to include some deletes? All right, tools. Okay. Well, wherever it came from, this is how it works now. All right, so here's vtable. Let's look at get rid of this stuff. pxd.pxi. All right, yeah, let's look at the vtable pxd. So we can copy pointer, destroy pointer, and compare pointer. And then we've got the cdef gRPC arg pointer vtable, default vtable. And here's the pxi. So we're going to link to an issue, reform this. Let's look at the issue. But we can copy pointer, destroy pointer, compare pointers. And that's pretty much it. Let's look at this GitHub issue that tells us we need to reform what's going on in the vtable stuff. Drop maintenance of references to channel args from channels and servers. It should be possible to have channel arguments get garbage collected when gRPC core is done with them, rather than having them have to be held for the entire lifetime of the channel or server. Channel arguments. Okay, but so far I haven't been successful. So it was fixed by freeing them, I guess. Let's do a quick search for a gRPC vtable to see whether this is maybe just talked about in the documentation. Because we looked at the vtable code before, but I didn't have a sense of what it was doing. Arg, channel arguments. Yeah, I guess not. Oh well. All right. We can move around pointers. Maybe this is just providing access to pointery virtual function stuff that people don't usually have to be concerned with. I'm not sure. Like, I guess to do dispatch, C++ needs to have a virtual table, some sort of object from which you can dispatch functions. And normally, I guess you just use what C++ does, but maybe this is a way to they seem to be trying to modify that table directly with code in the C++ core library. And so maybe that's the sort of thing that's going on. Don't know. But this whatever they're doing with the vtable stuff, this is like the Python. What we just looked at is the way to achieve that through the Python code. All right, so here we are in thread.pyx.pxi. We can check whether context vars are supported. And the method they use to try it and see if it works rather than predicting based on an interpreter version, etc. So you try to import it, and if it fails, you just return false. Okay. That's a nice pattern to see because, like, sometimes it's tempting to do that rather than try to intelligently detect stuff. And it's nice to know when, like, serious software does the same thing. Okay, so we've got this run with context, which runs a callable with context vars propagated. If context vars are supported, the calling thread's context will be copied and propagated. If they are not supported, this function is equivalent to the identity function. All right. Did we look at thread.pyxd? And is there one? No. Context vars. So what is a context var? Is this a gRPC thing or a C thing? Context var. Context variables. Python. Access to context local state. The context var class is used to declare and work with context variables. Okay. But what is a context? We have a PEP, a new context vars module, and a set of new C Python C API calls to support context variables. It's similar to thread local storage. That's basically what I was looking for. But unlike thread local storage, it also allows correctly keeping track of values per asynchronous task. For example, async IO task. So it's basically thread local storage, but it's somehow aware of the way that they do async tasks. Okay, so I'm going to think of it as thread local storage, but maybe nicer for Python, the Python world. Okay, and so if we're going to run with context, then we're just going to call it on a target, which is a callable object that we're going to wrap. And it's going to return the callable object with some wrapping with the same signature as target, but with context vars propagated. Okay, so let's see how we propagate it. So if we don't support it, we're going to do whatever this is. If we do support it, we're going to define run with context at target, which is this function. I guess we'll redefine it. We're going to get ctx from context vars.copy context. And then we're going to have this run function that we're defining, I guess, like as a sub function. And it's going to call ctx run. And then we're going to return the run function. All right. And then, so to know that the callable object with the same signature thing is true, you have to look up the type of ctx.run, which I'm not going to do, but some runnable object. Cool. All right, so here's the completion queue. Here's the completion queue. Not too long. Are we in the pxt file? Okay. So we've g-interrupt check period milliseconds. We have next, which is going to return a gRPC event. It's going to take a gRPC completion queue pointer and a deadline. I don't know what accept star is. I guess it's going to throw some sort of exception, and star is maybe all of the exceptions. I don't know. Or maybe it's just related to the pointer, the fact that there's a pointer here. Maybe that's like a null pointer thing. So at any rate, so that's a question about Cython. I could look it up. I'm not going to look up everything I don't understand because that's not, the point is not to understand everything. The point is to understand enough and not get bogged down too deep in the weeds. So we'll leave that there. Well, maybe we'll figure it out at some point. All right, but we've also got this interpret event thing, which is going to take a gRPC event, a C event. Okay. Latent event arg is a class that's going to be cdeft, which is going to have a completion queue pointer and a deadline. And then the class completion queue with a capital C and capital Q. I'm a little bit curious now why these sub things have to have cdefs, but I guess these are essentially nested structs, right? So I guess this is telling it to have the C struct somehow instead of making some other kind of object, like a Python object. And at any rate, the completion queue is going to have a pointer to the C completion queue. So the Python completion queue will have a pointer to the C completion queue, and Booleans saying whether is shutting down, like it's in the process of shutting down. And I guess is shut down is probably if it's completed shutdown. And you can interpret an event. But you can't do anything else with it. You can't like add something directly to the queue, I guess. You can't pop something from the queue. And that's what you can do. All right, so this should be the implementation of the completion queue binding. So next, I'm going to have this except star. Do we handle exceptions at all? Okay. All right, we'll look up except star. Look up Cython null pointer. Memory allocation, maybe? All right, Cython except star. Let's try Google. Except star. Okay. In Python, more specifically in the CPython runtime, exceptions that occur inside of a function are signaled to the caller and propagated up the stack through the defined error return values for functions that return a Python object, and thus a pointer to such an object. The error return value is simply the null pointer, so any function returning a Python object has a well-defined error return value. Okay? CDF function may be declared with an exception return value. Functions defined as C functions can return arbitrary C types. We do not have a well-defined error return value. By default, Cython uses a dedicated return value to signal that an exception has been raised. Okay. I still don't see except star. Okay. CDEF functions that are not extern are implicitly declared with a suitable exception specification for the return type. For example, except star or blah, blah, blah. All right. It still doesn't really tell me what except star is, but something to do with exceptions for sure. All right. Okay. All right. So so here's the underscore next function for the completion queue. Now we've got this G interrupt check period milliseconds. And we're going to have these C variables, C increment, C timeout, C deadline. C increment is going to be GPR time for millis. So GPR is like the, we looked at it before. It's the Google C runtime. And it's similar to the C++ runtime, but I think C++ is one more letter, and GPR with just 3 letters, I think, is the C runtime. I believe, but not positive. Okay, so we're going to check if the deadline is none. If it is none, if it is none, then GPR in future. So I guess the infinite future, but passing in a real-time clock. That's going to be the deadline. Otherwise, we're going to get the deadline from whatever is passed in. while true with no global interpreter lock. We're going to get the timeout, compare times, and do that. I don't know why we need to not have a lock as we do that. I guess, I don't know. Then we're going to call gRPC. I guess this is maybe why, because we call gRPC completion queue next on the C completion queue with the timeout and the null. And I guess that adds an event as the next event to the completion queue, probably, unless it's getting the next event. Well, it's returning an event. So, but what did we call it with? Just the queue and the deadline. So we're not adding an event. So we're getting this event. And if the event type is not gRPC queue timeout, so if we're not a timeout, or this thing is, or the timeout and the deadline compare to 0, so they're equal, then we're going to break. Otherwise, we handle any signals by, I guess, just calling check signals, and that seems to also handle them. And then we're going to return the C event. If we break, we have no I see. Break is going to exit the while loop. And that's going to allow us to return C event. But what happens if we never have anything? Yeah, I guess, I don't know what happens if there's nothing left in the queue. I guess C event is like null or something. Okay. We can also interpret the event. We're going to cdef underscore tag. We're going to check whether it's a queue timeout or queue shutdown. All right. Okay. So if it's a timeout, return none. What are we returning? Where's the return values here? I don't know. Do not co-opt connectivity event here. But we're going to return none and connectivity event gRPC queue timeout false none. Don't know what false and none do, but some connectivity event if it's a queue timeout. If it says the queue is shutting down, I guess, then we're going to emit, I guess, some sort of event that it's shut down with none. I don't know what none is. Oh, that none is the tag, if it was successful. Otherwise, we're going to get the event tag. And it says we receive event tags only after they've been inc-refed elsewhere in the code. Okay, so if we're here and we have a tag, an event tag, then somewhere else in the code, maybe in, I guess we're running on a Python server or client either way, so somewhere in the Python presumably, something has incremented the reference count, and so we're going to decrement the reference count here, and then we're going to return the tag and the tag.event at C event. All right. And then we have internal latent event and a latent event. And we've got this completion queue class where this is going to give us the actual, I guess, implementation of the class, whereas before we had the header. And when we init it, got some attributes, fork handlers, and gRPC init. I guess this is more threading init stuff. If shutdown CQ, which is passed in as an argument. I don't know why you would shut it down on init, but maybe because it's really passing a message to the underlying CQ. I don't know. But we're going to set some stuff and say it's non-listening. Otherwise, we're going to create for next. gRPC completion queue create for next. Set shutting down to false. Set is shutting down to false and set shutdown to false. And then we've got this interpret event function. Internal poll is going to call self._interpret event underscore next of the completion queue with the deadline. I guess that's polling for another event, the next event. And then we have a function called poll. We name this poll to avoid problems with CPython's expectations for special methods like next and underscore underscore next underscore underscore. Okay. So poll It has some G event activated stuff. Thread pull apply completion queue. Okay. And then otherwise it's going to call internal poll, which is what is up here. By the way, somebody told me that I jiggle the mouse around too much and it's distracting. I tried to do it in the last video, but I still ended up doing it a lot. I do use the mouse for highlighting, I guess, and gesturing when I'm thinking. So I'll try to figure out how to be mindful of that without, you know, while still having my usual style. Okay, we've got clear, and we've got we can deallocate some stuff, and gRPC shutdown. I guess it's hard to really tell without a text editor, but this seems to be the last thing we do in the dealloc function. So when we, if that's true, then I guess when we call dealloc on the completion queue, that's basically game over. We have no completion queue left, so we're just going to shut down, I guess. Here's call, and it's just got a cdef to a gRPC call, and a cdef list of references. And here's call.pyx.pxi. So we do this fork handlers in gRPC init thing, which creates init's going to create an empty call, but the first thing it's going to do is make sure that, I guess, multi-threading and communication to the C stuff is working. And we're going to set C call to null and references to the empty reference. And we can start batch, start client batch, start server batch, cancel, which has a long implementation, set credentials, peer, look at peer, dealloc, a property called isValid. This object should always be valid from Python, used for debugging, and custom op on C call. All right, so start batch is some sort of batch operation. So we have client batch and server batch. Okay, let's look at start batch. So we're going to make sure we're valid. We're going to batch operation tag prepare. We're going to increment the reference to the batch operation tag. We saw before that when we got a tag out, it had been, its reference count had been increased somewhere else in the code, and this seems to be one of those locations. We're going to, I guess, allocate an error, and with no global interpreter lock, we are going to call gRPC call start batch. We're going to call out to the C function. We're going to pass in the C call, the batch operation tag, .c ops, batch operation tag, .c no ops. I'm not sure how those are set. And whatever this is, a pointer to a Py object batch operation tag thing being cast, I guess, and then null. And then we're going to return whether there's an error. So this, I guess, is the actual call that sends stuff on the wire, I would guess. Or rather, it probably adds stuff to the queue. It adds calls to the queue, and that eventually sends stuff to the wire. Start client batch. We're just going to call start batch with false. We don't reference this call in the operations tag because it should be canceled when it goes out of scope. Okay, start server batch. We're going to call start batch with true. And the Boolean that differs between start client batch and start server batch is the third argument to underscore start batch, which is retain self. And it's getting, well, what happens to it? Okay, so it's used here. So self, if retain self, else none. So it's being passed into this batch operation tag thing. And if we're passing in self, then presumably what's going on is self is in C world, self is a pointer to the essentially the Python object, but the Python object like in the C code, I guess. So it's like a C pointer to the Python thing. And if we pass in retain self, this is going to, I guess, tell the somehow going to going to tell the garbage collection that we want. And this is another thing that has this pointer, and we don't want it garbage collected. And when do we retain self? We retain it if it's a server batch, but not if it's a client batch. I'm not sure why, but it does say we want to cancel if it goes out of scope. Okay. So cancel. I guess we cancel if it goes out of scope because this is just a guess, but we wanted to receive the reply from the server, right? So this should, even if we're doing async operations, there should ultimately be something listening for the server's reply. And we don't want to just like send something off and have nothing listening for the reply. Is that why we, I don't know. If we go out of scope, maybe that means that in practice we can't actually listen, so we don't want it to be retained or something like that. I don't know. Maybe somebody else knows. If you know, let me know. All right, and then cancel. Presumably this is going to just set some stuff up and then call out to the cancel function, the C cancel function with no global interpreter lock. If error code is not equal to gRPC status, do not use. Okay, but let's see what it does. We're going to give it a status code and set it by default to something that should never be used. So not changing it, I guess, is a bug or an error. We'll set details to none. Oh, no. By default, details is none, but you can populate it. And so we'll get the details as bytes because we're going to pass it to C. If it's not valid, we'll send we'll raise a value error. If there's something wrong with the details, we'll raise another value error. And we'll have the call error, we'll have the result, which is of type gRPC call error. And we're going to, I guess, populate the details. And then we'll call cancel the status. Or otherwise just call cancel. Okay. And set credentials is just going to set some credentials by calling gRPC call credentials, release C call credentials, or gRPC call set credentials. All right. And then peer is just a string and call get peer. So this is just getting the peer. And then dealloc is going to gRPC call unref the call. So I guess reference decrement the call, and then we're going to shut down if we dealloc the a call, I guess. What? I don't know. I guess that's what's going on. All right, so that's call. So I'm beginning to get a sense of how things work. There's not a lot of like pure Python. It's mostly just getting things to work with C. Let's take a quick look at AIO. I don't know if this is the same call I looked at before. Is there a call? Yeah, there's call outside of AIO and call in it. I think AIO is maybe adding support for a specific async IO framework, or maybe Python built in async IO. We've got AIO call of gRPC call wrapper. Yeah, read only AIO channel list references. Okay, AIO RPC status. Cool. Create gRPC call. Set status with an AIO RPC status. All right, so this is the PXD. And what do we got here? The PXI. We've got some error messages stuff. Get initial metadata, AIO call, AIO channel. Let's look at AIO channel. Is that a gRPC thing? Yeah. Let's see if there's a Python AIO stuff. Okay, so Seems like Python has like coroutines or some sort of async IO stuff built in now. Lib async IO. I don't know. I'm not positive if this is built into Python, but I think this might be relatively new. Let's see if Wikipedia will tell me anything. Coroutine. I think I misspelled coroutine. Coroutines via enhanced generators. Okay, this is actually relatively old, 2005. All right. Oh, this is just like yield and stuff. Does this also have async await? This is from 7 months ago. What if I look up gRPC Python async AI design? Let's see if there's a design. All right, here's the, it's a new version. Okay. The new version of gRPC Python, whose architecture is tailored to async IO. All right, the design doc can be found here as a gRFC. I'm just curious about the timeline. May 2020. All right, so this is just a few years old. Right. So this is just another way of making gRPC calls that interacts better with Python's async await framework. But we saw in the non-new version that there were some that the people authoring the Python bindings had to be concerned with things like threading, the global interpreter lock. So I would expect some of those concerns to be different in the async await place. And it also seems like async await was maybe re-implementing some stuff in Python that the standard Python implementation just used the C versions of. So there may be some reason why, like perhaps the async await threading model doesn't allow using the C layer as much. So that might be one sort of thing you would have to think about if you wanted to write bindings for gRPC in another language that has a built-in asynchronous or threading framework that may not be matching with what C or C++ is doing. All right, so I think that's basically it. I think did we look at underscore server? No, we didn't. Okay. So let's look at underscore server. Maybe typings. Do a quick glance at typing. Okay. If type checking, we'll do this stuff. Request type, response type, serializing function, metadata type, channel argument type, null array callback type, and some other stuff. And then what is this? Oh, wrong tab. All right, so we'll look at server.py, and I think that's it. I'll do a quick check to see if I'm missing anything major. But I think I have a sense of how the Python wrappings work. At least more of a sense than I did when I started. All right, so here's the server.py. This looks longer. Let's see how many lines it is. 1141. So 1141. Since we're at the bottom anyway, let's take a look at create server. It's going to take a thread pool. We get type information. That's nice. It's going to take a thread pool. It's going to take RPC handlers, which is a sequence. What is a sequence? I don't know. From typing import. I'm just curious if this sequence seems to imply ordering. Or maybe it's any sequence type or something. Maybe it's supposed to be like a family of types. Okay, there are two examples of sequence data types: sequence, list, tuple, and range. Okay. So this is like Python's way of talking about certain collections, list, tuple, and range. That by sequence, I guess it means it has some sort of like next operator, like a linked list, or a tuple, or whatever, or a range. Okay, so where are we? We're at the bottom here. Okay, so it's going to take a collection of RPC handlers, and you can kind of choose the collection because they kind of, as long as the type rolls up to this specific to this sequence thing. You're going to take a collection of interceptors, some options, which is going to be a collection of channel argument type of channel arguments. You can set the maximum concurrent RPCs and whether to use our compression. And XDS is a bool, maybe whether to use XDS. And it's going to return, I guess this is a thing of type _server. And what we're going to do is validate generic RPC handlers. It will validate them, and then we'll return the _server and just pass everything in. So do we have _server as a class? I bet this is it. Certainly is looking promising and very long. Oh, no, it's server state. Is this it? Call behavior. All right, I'll look for, I bet this is it, but what is it? Class _server maybe? All right. So here's class _server, and we've got a server state. And we can init with all the stuff that we just talked about. And we get a completion queue, I guess creating a new one. The server is we're going to call side gRPC server to get the Cython-ish server implementation. And we're just going to stuff that. I guess that's just going to be like a variable inside of the Python _server thing. We're going to register the completion queue, which makes sense. We've got to figure out where the completion queue the server needs to know which queue to use. We created one, but I don't think the server knew about it yet. And then I'm going to set state to _server state. With the completion queue, the server, the generic handlers, the interceptor service pipeline full of interceptors, the thread pool, the maximum concurrent RPCs. So server state seems to be that might be the I don't know. Is that the more important thing? We'll see. We'll look at both. We can add generic RPC handlers, and we just validate them and call add generic handlers. Right. And to add the handlers, we pass it the state. We don't pass it the server. The state already has the server. We can add an insecure port, and that just calls the _add insecure port. And again, we pass in the state and not something like the server. Okay, we can start, and to do that, we call _start on the state. We can wait for termination. We can stop, we can del, we can has attribute. All right, so let's look at server state. Here's the server state. All right, we've got a lock, threading our lock. We've got the completion queue, the server, which we passed in when we created it. The handlers, the interceptor, thread pool, termination event, shutdown events, maximum concurrent RPCs as an option, active RPC count, do, is that different from deadline? A list of RPC states and whether the server has been deallocated. Okay. So the constructor is just going to set up variables that are passed in, set the RPC states to the empty set and set do to the empty set, and we have a to do to eliminate these fields. And there's a volatile flag to interrupt the daemon serving thread. Okay, how do we know it's volatile? I'm not sure. All right. So with underscore add generic handlers, which takes the server state and the list of handlers, we're going with the state.lock, which is this thing. It's a threading lock, I guess, from Python, as opposed to like a C lock, I think. So we're going to lock the stuff, the Python stuff, and we're going to say state.generic handlers extend. So we're just going to add, we're just going to like add them to the end of the list or whatever, the generic handlers. So add in secure port is going to just do the same thing. Essentially, it's going to add HTTP2 port, but without credentials. So add in secure port and add secure port just differ by whether they call add HTTP2 port to whether they pass credentials to that function. We can request a call. I don't know what request call does, but it takes a completion queue and a request call tag. They do add request call. Let's see what request call does. Server request call. Does the server request the call? So this is Python. I don't want Python. I don't know. gRPC server request call. Oh, is it just it can mean immediate failure on the request call? I think this is just request in the sense of like it's a gRPC request and it's a call, I think is what it's saying, as opposed to like I was thinking initially that this was like requesting a call object. I've been thinking so much about objects and structs and stuff. So I thought that maybe this was like asking for a maybe like a reusable call object. But maybe this is just sending for making a call that's a request to the server. I don't know. Okay, so stop serving. That's straightforward. On call completed. I guess this looks like a callback. It's going to take a server state and it's going to lock the Python stuff. And we're going to set active RPC count. We're going to decrement active RPC count. So that's just keeping track of statistics essentially. Process event and continue. This looks interesting. Okay, so we're going to give it the state, the server state, and the side gRPC base event is going to return a bool, probably whether it's succeeded or failed. So should continue is true. We're going to check if it's if we need to shut down, in which case we set should continue to false and actually shut stuff down. If the event tag is a request call tag, then we're going to lock the state. We're going to remove the request call tag from do. Oh, maybe do is the things that still need responses, like the obligations in some sense. So we're going to check if concurrency is exceeded, which is maximum concurrent RPCs is not none, and active RPC count is bigger than or equal to the maximum concurrent RPCs, in which case, regardless of what's given, regardless of whether concurrency is exceeded or not, we're going to call underscore handle call and pass in a bunch of stuff, including the event, the handlers, the intercepted pipeline and stuff, and whether the concurrency exceeded or not. And I guess handle call will just decide what to do about the exceeded concurrency, if anything. And that's going to give us back an RPC state and an RPC future. So if we have a non-RPC state, we're going to add it to the list or the set of RPC states. And if we get a non-trivial future, we're going to increment the active RPC count. And we're going to add a done callback, namely the onCompleted call, which is going to decrement the count. Lambda unused future. Unused, I guess, in the sense that we're not going to call it directly or something. Seems to be used. If state stage is server stage started. Okay. What is state.stage? Well, from the started stage, I guess we're the server and we've started. Then we're going to call request call and pass in state. Otherwise, we're going to stop serving. Okay. Else, if it's not the request call tag, it's some other tag. We're going to get the RPC state and callback by calling event.tag event. And we're going to iterate over the callbacks and try to call them. And if RPC state is not none, we're going to lock the state. We're going to remove the state, I guess we just got back. So if we're done here, then it seems like we're done-ish because we're executing the callbacks, which seems to imply we're finished with whatever work we were doing. And we're removing the state. And we're going to stop. If we need to stop serving, then we said should continue to false. Otherwise, we return whether we should continue. Okay. And then serve is going to say, while true, we have this infinite loop. We do timeout event is equal to state.completion queue poll timeout. So we're going to get the next event by passing the timeout. If the server's been deallocated, then we're going to shut down. If the completion queue type is not queue timeout, I guess, and if not process event and continue, then we return. So these are both negated. So if it is queue timeout, then this negation is false. And if it is process event, if process event and continue says we should continue, then this is false. So this checks whether process event and continue returns false. That means that this function thinks we should essentially shut down, in which case we do exit the infinite loop. Otherwise, we set event to none, and we go back to the top and look at what the next thing in the queue is by polling it. So if I'm understanding this correctly, the serve function just on an infinite loop reads things from the completion queue and does what with them? Possibly shut down, otherwise sets it to none. We want to force the deletion of the previous event before we poll again. If the event has a reference to a shutdown call object, this can induce spin lock. Okay. So we want to avoid spin lock. But what do we actually, so process event, okay, right. So let's see. This is, I guess, process event and continues the thing that processes the event. So, so this is checking if it's a timeout. If it is a timeout, we don't go here. If it's not a timeout, we do go in here. And either way, we call process event and continue. But depending on the result, we might return. So this is a little bit hard to read because it looks like it's doing a comparison, but really it's executing this massively important function. It looks like that's doing the real work of like making this thing be a server, and it's kind of, but that's kind of hidden in this like conditional statement. So I'm not sure if there's like a performance benefit to this, but I think just in terms of readability, this may not be the ideal, but that's okay. It's understandable at least. All right. Then we've got begin shutdown once, which is going to look at the lock stuff and manage state and whatever appropriately. Stop is also going to do similar things. We're going to set the lock. set state to stop, do some threading stuff. Okay, and start, what is start going to do? It's going to get the lock. It's just going to manage state, I guess. State server start, state stage is server stage started. And then we're going to call request call on state. And then we've got this thread. Okay, so threading.thread target equals underscore serve, args equals state, thread daemon is true, and then we're going to start the thread. Okay, so this, I guess, is starting the serve operation on a separate thread. And we can validate the header, the handlers. We're just looking at Python attributes to do that, it looks like. And we've got argument options. And that's basically it for server state. So let's look at request call again. Where does this function? Okay, so here's request call. So so the state.server, we're calling request call ultimately on the server. And we're passing the completion queue and also the completion queue and the request call tag. And yeah, okay. So what is the I thought that the state okay, so state.server request underscore call. So is there no request underscore call definition? Look at the class server again. Server. Okay. Well, I'm not sure where the actual request call is defined, but it seems like we call request call as soon as we execute. Let's see if GitHub will let us search request underscore call. We've got some fuzzers. We've got some Ruby code, some end-to-end tests, server tests, Ruby stuff. Python stuff. Maybe is it? I forget what the convention is for C code. Is it like that? Request call. Here's PHP. Async generic service. Looks more promising. All right. Server notification. Request async generic call. Look at servers CC. We have async request, but not request call. Do we have request underscore call? Maybe. But that seems to be the same thing. The following call start batch is internally generated, so no need for oh, maybe it's part of the generated code. Okay. Let's try one more time to search. Server. So I don't want .py. I don't want Ruby. This is a Chromium PHP thing. Let's try maybe without the underscore. Let's try with no space. Okay, so here's an example of, okay, here's the function. And we're in the CC. So this is in lib slash, okay, so the gRPC repo, but we're in source slash core slash lib slash surface. Surface as in like the surface of a table or something. And request call is going to take a call details, request metadata, and some completion queue stuff, CQ bound to call and CQ for notification. And we're just going to call a new requested call, queue requested call. So maybe this is when a server receives a request. Let's see if they have the H file. What was it called? Requested call? Private struct requested call. Publishes an incoming call to the application after it has been matched. Yeah, I think requested call or request call is like an incoming call. Seems to be all that means. Okay. All right. So let's get on back to the Python code. All right. I think that's mostly it. There might be some client thing here. Let's see if there's an underscore client. But that seems to be the stuff that's in the gRPC thing. We'll look at these directories just to make sure I looked at them. So we've got common foundation interfaces. What is foundation? Abandonment, callable, future, logging pool, stream util. Let's look at the stream thing just real quickly. Common, cardinality, style, and what else? Interfaces, base and base. All right, that doesn't seem so monumental. Stream.py, interfaces related to streams of values or objects. So we've got a consumer interface for consumers of finite strings of values or objects. And we can terminate them and consume and terminate and raise a not implemented error. All right, so that's stream stuff. This is experimental stuff, includes AIO, some G-event stuff, a session cache. Beta is beta, stuff that's in beta. I think you looked at AIO. That's essentially like a parallel implementation, if I'm understanding correctly. And then this is just the side gRPC folder that we looked at. Is there anything that I really feel the need to look at here? Operation propagation bits. Let's look at propagation bits, I guess. Security tag. Maybe a quick look at tag. Did we do that already? I don't know. Okay, so propagation stuff is like, okay, like deadline, census, stats, cancellation defaults. So stuff that needs to be propagated. All right. Basically just definitions. And here's tags. We've got a tag, connectivity tag, request call tag, batch operation tag, server shutdown, and similar stuff. All right. So that's the gRPC Python bindings. Hope that was interesting. Hope you had a good weekend, and I'll see you tomorrow. Thanks for watching.